Okay, so here's what we have left. And they're all kind of eventually going to be tied in together. So we've got circuits, and then we have magnetism, and then we have like quantum mechanics. So we have 3.
7 weeks.
Huh?
7 weeks.
That's not bad. That's 2 weeks for you. How much is there around?
Yeah, physics. You know what? I'd be down.
Oh, so
It
that's
sounds
not
easier.
bad.
It sounds better.
The tism though.
This might be. This semester might be.
Okay,
Yes, the tism.
This
so
semester might be okay.
We are not.
So when you talk about circuits, there's 2 kind of ways we deal with circuits. Like a theoretical one, and we're going to use them kind of because we use this a lot. So if FET has a nice simulation of
You said
circuits.
that so loud. There's a fit.
Yeah. Wow. I've done that before.
What?
Berg, is this real or is this a little boring?
No.
Take him out of the contract.
Did you listen your voice? Yeah.
I did this engineer.
I already lost it last week
Okay,
from coughing.
so let me kind of
Wait, so you're
explain
No, I wasn't.
what circuits
Oh,
are
so I
and
was
what
like,
we have wrong
but I was just
about
like,
circuits in terms of conceptions and
I
things
was
like
like,
that. So, and we're going to use this program a lot, so it's kind of cool. Like you can drag the battery, okay, and you can. The purpose of the battery, it is both right and wrong in terms of this story of how it works. So the purpose of the battery is if you imagine electrons traveling in the circuit. So it's a visual, and some people like this. It's really not accurate, but some people like this. So the purpose of the battery is that these electrons are sent out, and they go out and they do work. They go through the resistor, they make toast, they run a light bulb, they do something, they do work, okay? But when they do work, it costs them energy. And so what the battery does is that when the electrons come back in, and imagine that there are these little guys going out to do work, and they've got like their little lunch pail, right? So the electrons are going out, they've got this lunch pail. And when they do work, they eat the food that's in the lunch pail. They're tired when they get back. And they don't have any food because they used up all their energy in the food and doing work. And they get back to the battery, and the battery says, hey, buddy, I got you. And the battery then recharges them and refills their lunch pail and sends them back out to do more work. So there's also a book, it's a book called There Are No Electrons, which is an interesting title for a physics book. And if you ever read that book, they talk about greenies, and greenies are like the electrons, and it's kind of a similar type story. And they tell the story of greenies as like being like these homeless people that walk out and they're carrying the stick with their bag of food, and they use the food, and they come back to the homeless shelter and they give them food, and they complete the cycle. And that kind of works. Another analogy that you can make is water, where you turn on the light switch, and that's like opening the valve on a hydrant, and that allows the water to flow through. And as long as the circuit is complete, that's flowing. So the purpose of the battery is to provide a power source. Now, you can add some things to this. So you can take a wire, drag it, boom, okay, all right. And then let's say that we want to add a light bulb. Cool. And we'll put another wire here. And some people, when they build circuits, get very particular. Like they want everything to be like at nice little 90-degree angles, okay, where everything's parallel. And some people just kind of go crazy and go, oh, I'm just going to do whatever.
That's right.
That's fun.
Or what
Right?
type of guy are you?
which kind of guy do you think I am?
You're a 90-degree.
Oh,
You're all
absolutely.
crazy about it.
Yeah.
I am all about, it just flips me out. Yeah. Now, I'm not getting a protractor out and measuring 90, but yeah, it has to be
Almost.
Yeah.
Get that projector.
And then we can take a wire, we can connect it, and we can throw in a little switch here, we can throw a wire
What is
here.
happening? I don't know.
Okay. Right?
It's not perfect.
And then we close the switch. Oh!
Oh my god.
Yeah, no, that's
Okay.
Well, this is crazy.
Now, here's the problem. And this is the direction of the current flow. And every year I give this speech, and kids flip out. Not necessarily flip out, but they become agitated. So the problem with the conventional idea of electricity, this is what we use, and don't sit there and go, well, where it's wrong. I don't care. This is what we use. You all don't get to vote. Okay? So if you go back to the days of Ben Franklin, well before we knew anything about electrons, protons, neutrons, electric field theory, anything like that. So Franklin's famous little, what he's known for was the kite and the electricity and the string and all this stuff. And so Franklin was a diplomat, but he was also like kind of a and basically Franklin had a 50-50 shot. He saw things as being positively and negatively charged. And so Franklin said, and that he had a 50-50 shot, and he said, I think electricity is caused by the movement of positive charges. Okay? So by conventional standards, and don't say that, oh, that's not right. We don't care. Okay? This is how it's defined. Even if you look at your equation sheet, okay, back here on the bottom, it says on here in this box, it says the direction of current is the direction in which positive charges would drift. Okay? Just so everybody's cool. So on the AP exam, when they talk about the movement of current, they're talking about the direction the positive charges move. Now, don't sit there and go, well, why do we keep it? It's wrong. We keep it because it's always been done that way. And it's really, and here's the argument that you can make, right? You can kind of make the argument that it's true, because if you look at what creates an electric current, there's certain things that have to be completed. Number one, you have to have a completed circuit, okay? Because if the electrons can't make it all the way around, hey, sorry, you can have the potential to move, but it's just like you want these people to go around on the circuit, but the bridge is out. And if the bridge is out, you can't go all the way around the loop. So you have to have a continuous circuit. And the other thing that you have to have is some source of energy, okay? Whether that's the grid, whether it's a battery, whatever that is, okay? Maybe it's a hand crank generator, whatever it is, you have to have something to make them move. So there's two things wrong with this model, okay? First off, it shows the movement of positive charges. And again, don't sit there and go, what's wrong? Positive charges don't move because they're bound up in the nucleus. This is why you don't drift positive charges, because it's like the St. Bernards and the Chihuahuas. The St. Bernards are locked up in the nucleus with the sheepdogs. They're not going to go anywhere. It's the Chihuahuas that move, okay? But Franklin said, this is what we're going to do, and everybody said, cool. We, with a shout out and respect to the elder statesmen, we kept it that way. That's why. Now, here's how you can kind of make the argument that it still works. So, and again, this is still going to be wrong, but stay with me. So if you look at like good conductors, like copper is a very, very good conductor of electricity. So if you look at this, if you can look at this on an atomic level, you'd have the nucleus of the copper, and then you'd have these electron clouds of the Chihuahua clouds around it. And so one of the things you can talk about is what's called electron drift. So what's happening is that as you apply a voltage. Okay, if you remember voltage, anybody remember the units for voltage? Joules per kilo. So voltage is how much energy there is per unit of charge. So something has to provide the capacity or the desire for the current to move. A battery, a generator, something. So if you look at these electrons moving, okay, so let's say that the current is moving in this direction. So now what we understand is that it's actually electrons that are moving. But even that isn't necessarily an accurate description of what's taking place, because electricity moves very, very quickly, which is a good thing. If electricity travels slowly, I would walk in and turn on the light switch, and if the electricity took a while to move, there might be a delay between when I turn on the light switch and when the light comes on. Yes.
Or in the gymnasium, you turn the light switch on, it takes like 3 minutes.
Well, that's because they have to warm up.
Oh, okay.
It isn't because
Okay, thank you.
Wait, why do they have to warm up?
Because they're cold.
especially if they're what they call mercury vapor lights, those have to warm up. Basically, they have to warm up to excite the electrons enough to start. Okay.
What's a mercury vapor?
So the electrons themselves drift relatively slowly. The electrons are not moving at the speed of light, but the current travels at the speed of light. So one analogy of electricity is that, like, you have a hose and here's your hydrant, okay, and you turn that on like when you open up a switch, and then the water moves through the hydrant, okay, or through the hose, and it goes to this, whatever you want to do. And it's how fast the water is moving itself is how fast the individual particles of water are moving. So if the flow rate is 5 meters per second, that means the water itself is moving at 5 meters per second. Electricity doesn't work that way. We model it, we like to think of it that way because it kind of makes sense. So like, oh yeah, I connect the circuit and then something is pushing the electrons through. Now, I'm not saying the electrons don't move. That isn't the point of the story. What's happening is when the electrons move, they propagate an electric field that travels through the wire. It's the electric field itself in conjunction with the movement of the electrons that creates the electricity. Okay? So we model it, we draw little electrons that are moving, okay? But the electrons themselves are not moving at the speed of light. Now, this is where you can kind of make the argument that Ben Franklin was still right. It's a stretch, and I'm going to tell you it's going to be a stretch, but stay with me here. Okay? So you turn on the switch, okay? You hook up the battery, whatever happens. And the electron moves from one Chihuahua cloud to another. So what happens is that now there's like a hole where the Chihuahua was, okay? So there's a deficiency of a Chihuahua. So there's, if you imagine it's like a hole in the Chihuahua cloud. Well, then something has, the next Chihuahua then has to come in and fill that in. So, but then that creates a hole to the left, and it perpetuates that way. So if you've, like I said, this is a stretch, but it's, they're trying to save Ben Franklin's reputation, okay? So if you look at the electrons moving in one direction, but the propagation of the holes, which would be like a positive charge because you have the deficiency of the electron. So the propagation of the holes in the Chihuahua cloud is moving in the opposite direction that the electrons were moving. Okay? I didn't say it was the best story, but that's how they tried to save Ben Franklin's reputation. It's like, well, he wasn't entirely wrong, because when an electron moves, that creates a net positive, and so another one has to fill in, and then that starts this cascade. It's a stretch. Don't worry about it. So here's the whole point of the story, is that when we talk about circuits, when I say a circuit, the circuit's going in a particular direction, what we're assuming is that we're using the conventional idea that it's positively charges that are moving. So on this, and we're going to use this simulation a lot. So you have a positive and negative terminal. The easiest way to remember that this is the positive terminal is that because it has like a little knob that sticks out, that almost like makes like a small plus sign. That's the easiest way to remember that that's the positive terminal of the battery. Now, if you go to movement of the electrons, and again, this kind of perpetuates this false idea that it's the electrons that are traveling. The electrons are moving. I'm not saying that. But the electrons themselves are not traveling at the speed of light. Okay? It's the electric field that they're perpetuating, propagating. That's what's actually moving through. So it's a combination of the two of them. You do have to have the electrons moving, but the electrons aren't moving that fast. Okay. So this is this nice model. It's great. Okay. You can have light bulbs and all of this stuff. Now, the beauty of this program is that the wires have no resistance. Okay, so these are like perfectly non-resistance wires. So the only way you lose electricity or you lose this energy is it goes through a resistor, it goes through a light bulb, it goes through something like that. Okay. The batteries don't have any internal resistance, so that's a cool deal. So this is very much a perfect example of, like, you know, when we talked about acceleration due to gravity, we drop something, and we always use 9.8 meters per second squared. We neglect air resistance because that just makes things awkward because you have to deal with it. So the same thing is true with electricity. Unless you're specifically told to worry about the resistance in the wire, don't. Okay? You assume that you're only going to lose electricity going into like a light bulb or resistor or something like that. Okay, now, so that's just a simple light bulb. Now, you can also have, chill out. So you can also add a resistor. Now, okay?
Slow.
Oh, slow down. Okay? So, when you look at the units that we're going to use to measure stuff in electricity, one of the most important words or most values things we measure is current. Okay? And for those of you who've been in AP chemistry, you've already seen this. So, Nathan Nelson, what are the units for current?
Amperes. Amps?
Campers?
Amperes. Is it amps, amperes?
I thought you said campers.
What?
I swear to God, I thought you said
No,
campers.
amperes.
Yeah, that would be something.
Like
Okay.
A.
I think it's
A is in like atom.
Which is also measured, but what fundamental
Oh,
units?
amps. Amps.
Angry Blair will get
It's something per unit of time.
Isn't it
Coulombs
coulombs?
per second.
Coulombs per second.
He was just joking.
That's what I
Really
thought.
gonna do it the whole
I
time, bro.
literally,
Too slow.
I thought you said campers, so I thought you were going to go like campers per second. That's where I thought you were going with that. Okay. So
Amps per second.
it's measured in amps, right?
Amps and then it's coulombs per second.
Which is
Second.
coulombs per second. Right? Cool. Now, here's an analogy that you can make with electricity. It's not a good one, but it works. So imagine that you have a big concrete dam. And the height of the water is the voltage. Okay?
Wow.
So voltage is measured in what? No,
Joules per coulomb.
joules per coulomb. Okay? So the height of that determines how much energy there is. So if I go back to here and I'm going to measure voltage. Now, I'll go back and I'll show you how this actually plays out. So when you measure voltage, you measure voltage across like 2 points. Okay? So this is a
What?
9-volt battery. Okay? So the more that voltage is, the more energy it can give it per coulomb. Okay? So 9 volts, 18 volts, whatever that is. Okay? It's how much energy it's giving it per coulomb. So when those electrons are tired and they come back through and they need energy, the bigger the battery is, the more energy it can give to the electrons as they go around. Okay? Now, same thing has happened with the car. Okay? Typical car batteries are like 12-volt batteries. Okay? Typical car batteries. But if your alternator goes out, quick lesson in auto mechanics. If your alternator goes out, which recharges the battery, what happens?
Your battery
You
dies.
can't.
Your battery dies. Why?
Because nothing charges it back.
Yeah.
It just shoots it away.
So basically what's happening, if you go with the food analogy, a battery only comes equipped with so much food.
Really?
Okay? So then as the electrons go through, it depletes the food that's in the kitchen. So what the alternator does on your car is that it resupplies the food back to the kitchen.
That's the one with the belt.
Yes. Okay? Belt-driven system. So the alternator puts food back into the kitchen. Now, you can also measure voltage like across the light bulb. Okay? Now, so notice that is 4.5 volts. Okay? 4.5, right?
The resistor.
And then if I measure across the resistor,
Wow.
Oh,
it's also 4.5. Okay? Now, don't look at that and go, oh, that's cool, right? So each one is half of it, right?
Yes.
So the other thing that we're going to talk about is what's called resistance. The light bulb has a certain amount of resistance. The resistor has a certain amount of resistance.
No way.
Now, resistance is measured in ohms. So if you look at this in terms of water flowing out of the dam, so you can have a very narrow, like a drinking straw, or you can have a big concrete pipe.
Damn.
So in both situations, they have the same voltage. The water level is the same behind the dam. So the size of the pipe tells you the current.
Caleb. I can't believe you.
So
No
you can
way.
have a
I
drinking
actually was, I was
straw,
like,
you can have a big concrete
No
pipe.
way.
In both situations, the voltage would be the same, but the current would be completely different. So, as the old adage goes with electricity, voltage doesn't kill you, current does. Okay? It's the amount of charge flowing
this is a
through the
regular
pipe. So you can have a really high voltage, like the Van de Graaff generators that we use, that might generate 10,000 volts.
What?
But it's a very, 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 very small amount of current. But your house electricity might be 15 amps.
Oh.
Okay? Yeah. But you touch that and you get shocked. If you have never done that, I don't recommend it. So what resistance does, resistance is how it impedes the flow of that. So you can make the analogy of people moving. So let's say that someone has dropped off Chipotle for you down at the office. Okay? So you have a certain desire to go down there to get the Chipotle. Okay? So that would be like your voltage. Okay?
My speed.
Now, versus as opposed to someone drops off like a bowl of cooked spinach. Okay? Not so much voltage. Okay? Versus Chipotle has very high voltage. So the resistance would be how many people you encounter on your way to get the Chipotle. Okay? So we'll get more into this later. The temperature affects resistance. So, yes. So at high temperatures, people are running around and jostling. So you're trying to get down to the kitchen or down to the office to get your Chipotle. And the house and the hallways are crowded with all these hyperactive little freshmen. So you're going to run into a lot of resistance because the freshmen are impeding your flow. Okay? So you can't get down there as quickly. Now, in contrast to that, we're going to have freshmen out in the hallway, but it's going to be really, really, really cold, and the freshmen are going to kind of stand there like this going, wow, it's really, really cold. Where's my phone? Okay? So they're not going to have as much resistance. You're still going to have the same desire to get to the office to get your Chipotle, but your resistance is going to go down because the freshmen aren't moving around as much. Okay?
I see.
Got that.
I see something.
Now, when you look at, and we'll talk about all of these equations. So if you look at this section on your electricity, okay? So when you look at this I, that's Q over T. So this is why current has the units that it does, because that's coulombs per second. Okay, so that's kind of your bread and butter one. Now, the other one that involves current is delta V over R. Okay? So delta V is your voltage, R is your resistance. Now, they write it like this. The easiest way to remember this is that you vert it up. Okay? If you solve for voltage, that's the most common way to remember it. Why they write it as delta V over R, I don't know. Maybe they want to say okay?
V is what?
Voltage. Okay? Now, sometimes you'll see voltage written, it means the same thing. It'll be this fancy E. So if you get over here to like this magnetism unit, like over here where it has this, over on this it has E equals BLV, which we'll talk about that when we get into magnetism. So this fancy E stands for EMF. So EMF stands for electromotive force. So EMF and voltage mean the exact same thing. Okay, it's a desire for the electrons to move. So you could also see this written as I equals this fancy E over R. It means the same thing. So electromotive force and voltage mean the exact same thing. Okay. So we've got the circuit. 4.5, right? And we've got a switch. We open up the switch. Hey, nothing. The voltage drops to 0 because we have no current. Now, this is this nice idealized world. So, Mara, shut down the camera and let's go look at reality.
Oh, yeah.